So good morning all of you. I hope today I will be able to finish discussion on the chapter ion implantation. Only one topic is left, that is application of ion implantation in a particular area of buried insulator, and in that application we use high energy high dose implantation. So high energy high dose implantation, there are two applications. One is buried conductor, another is buried oxide and nitride isolation. So here the high energy and high dose. High energy, this value is typically 100 to 300 keV, and high dose, it is in the range of 10 to the power 18 per centimeter square. So that is a high energy high dose. There are two cases, one is buried conductor and buried oxide or nitride isolation. Buried conductor means some metal ions at high energy is implanted inside the crystal, and then you will find not at the surface but at a particular depth from the surface, you will have some metal conducting layer, and which will help in fabrication of latch-up free CMOS without epi layer. So nowadays epi layer has been introduced in CMOS technology, and because of the introduction of epi layer, we can have the latch-up free CMOS technology. But in some cases, that means in earlier cases where the selective epitaxy or epitaxy method is not used at all in CMOS, in those cases sometimes buried conductors are used to prevent the latch-up in CMOS. And the other application is buried oxide or buried insulator. So buried insulator means some dielectric layer is formed inside the semiconductor crystal. So here you can have buried insulator either or buried conductor, because in case of implantation you have seen the profile is the fully Gaussian. That means at the surface you can have the peak concentration is not available. Peak concentration of the dopants is available at length Rp, which is range value, and Rp is not at the surface, is at a particular depth. The Rp is dependent on the energy of implantation. So by changing the energy, we can have this layer, buried layer, inside the bulk crystal, and that particular layer can, if it is a dielectric, so it will have an insulation between the top layer and the bottom layer of the semiconductor. Okay, and this particular technique sometimes used in several process, and I will discuss in detail some of that process, which is SOI process, SOI technology. And there are two methods which is known as SIMOX. You may have heard the name of SIMOX technology, and also SIMNI, SIMNI, which is Si3N4, silicon nitride formation, and in some cases silicon dioxide formation. Okay. Now here a diagram is shown where 160 keV nitrogen is implanted into silicon before and after annealing at 1200 degree centigrade for 2 hours. The profile is shown here. So before anneal, the profile is shown in the dotted, not in solid line, not dotted line, and after annealing it is the dotted line profile. Now you see the depth, because the depth of penetration is after implantation, it is somewhere 2000 angstrom to 4500 angstrom there, and from the surface during annealing some of the atoms are out diffused from the surface, so that is going up, and here that some are going down here and some are going up, evaporation. So as a result of which in this region you can get clear silicon, and at a particular depth, means nearly 2000 angstrom to 4500 angstrom, you will have a layer which is the Si2N or silicon and nitrogen complex layer, which may form silicon nitride. And again, after the depth of 4,500 angstrom, you are again this oxide has not formed, because these movements will be there. So below that, for example, below say 6,000 or 7,000, you will get again silicon. So this side is silicon, this side is silicon, and in between at the middle you are getting a nitride layer. So that is the dielectric layer. So that is not possible by diffusion process, it's possible by implantation process, because here profile nature is completely different from the diffusion profile. There you get half Gaussian, and here you get full Gaussian, or in some cases Pearson 4 distribution is also like that, that at the surface you will not have much concentration. For high energy values, if you have low energy, then you may have the concentration something like this here, but if high energy means here is a high chance during annealing from the surface some of the impurity atoms will come out, evaporate, come out of the surface, and again some will go deeper inside. So as a result of which you can have a semiconductor layer at the surface. Okay, so this is the thing of high energy high dose implant application. Now I will discuss one application, that is the buried conductor, and that is basically the SOI technology. SOI technology is known as silicon on insulator. Okay, silicon on insulator, and there again the same method, high energy high dose implantation, is used in SOI technology. And there you can see a silicon layer is there, and the top is silicon and the bottom is insulator Si2 Si3N4, and the bottom is again silicon. And what you are implanting? You are implanting oxygen or nitrogen you are implanting, and then you are after annealing, in the middle layer you are getting an insulator film, in the top is silicon and bottom is also silicon. That is known as silicon on insulator. That means this is something, this is insulator layer, and this insulator layer is silicon dioxide or silicon nitride. If you implant oxygen ion, then anneal, then it will form silicon dioxide. But if you implant nitrogen ion and you anneal it, then it will form Si3N4 silicon nitride. So the silicon layer on insulator, so that is known as SOI technology. Okay, silicon on insulator. So now when you implant nitrogen, then this is known as SIMNI, SIMNI. Okay, and this is actually, the whole name is silicon separation by implantation nitrogen ion. Okay, and the other is SIMOX. SIMOX is very popular, and its full name is separation by implanted oxygen. Separation by implanted oxygen. This is SIMOX, SIMOX, SIMOX technology. Okay, and this SIMOX technology has got certain advantages. And the SIMOX is basically a process to form buried oxide by oxygen implantation. SIMOX is a process to form buried oxide by oxygen ion implantation. It will form buried oxide. So like this. So it has got several advantages, SIMOX, and those advantages are here: increased radiation hardness, increased circuit speed, increased packing density. So these are the advantages of SIMOX. Radiation hardness, increased circuit speed, increased packing density. So increased radiation hardness. What do you mean by radiation hardness? This is very important when a particular chip is used in space shuttle, or in some aviation vehicle or something like that, or that means in space, when you are going to use some chips, particularly CMOS chip, then the problem is in the space lot of radiations are available, that is alpha ray, alpha, beta, gamma ray, etc. Those radiation, when those radiation are penetrating into the silicon bulk, then there is a high chance of forming any ions inside the silicon. That means some of the neutral dopants or neutral silicon or neutral metal or whatever it is, they may be ionized by absorption of radiation, and those will again take part in conduction mechanism inside the silicon. So automatically the reliability of those chips will be changed. Okay, reliability will be poor, because after absorption of radiation, if the carriers are generated and those will take part, then obviously in CMOS technology, the threshold voltage, which is very important parameter in CMOS or NMOS, that may change. If threshold voltage changes in case of, for example, digital application, so many of the function will change. It will create some problem. So that's why particularly the chips which are used in radiation environment, and that is in space, lot of radiations are there. Even in the ambient, if you want to have some instrument and you want to use some chips, those are in say nuclear radiation environment. So there, this is the one important parameter. The chip should be hardened to radiation. Okay. So if there is a dielectric, you say, then the dielectric, there is a less chance of ionization. If it is a semiconductor, say electrons and holes will be formed by ionizing something, isn't it? That's why the buried dielectric, if the whole film is surrounded by a dielectric film, whole layer of the device, that means in case of BJT, collector, base and emitter, in case of MOS, source, drain, gate, and the whole region, inside the bulk silicon, if it is surrounded by a dielectric layer, and in the top if you put some radiation hardened film, so then that is protected from radiation. That is known as the radiation hardness. So this SIMOX technology is very useful, because using this technology you can form a buried insulator, either silicon nitride or silicon dioxide. That buried insulator will prevent that the deterioration of the performance by radiation, absorption of radiation. Okay, that is one advantage in case of SIMOX technology. And nowadays SIMOX is very popular technology, and it is used all radiation hardened chips and CMOS VLSI process. In many of the CMOS VLSI process, we use the high energy, high dose implantation for making buried insulator. Okay, and the next is increased circuit speed, and at the same time increased packing density. These two are related effect, and here that is achieved by the dielectric isolation. And as I mentioned, that the dielectric and isolation is advantageous for high speed circuit and high density circuit compared to that of junction isolation, because junction isolation, it takes a lot of area. You know what is junction isolation? So a lot of area in the lateral side, so automatically it will consume a lot of space, bulk, volume in silicon, so density cannot be increased in junction isolation technology. And at the same time, each junction which you are making for isolation, that junction will contribute some capacitance, that is the diffusion capacitance, and that diffusion capacitance will contribute some delay. Resistance and capacitance RC product will give you the delay, so that will hamper to increase the speed of the chip, speed of operation of those devices. So rather, if you use the dielectric isolation, the whole device is, because one device and other device, in between the layer you filled with dielectric, not only that, substrate and the buried layer. So there, if you put a dielectric film inside the silicon, then what is happening? Then whole area is covered by dielectric. The low cost process, what I have discussed earlier, so there on the side wall junctions are replaced by oxide, but not the bottom one. But with the advantage of the SIMOX process, the bottom means I mean to say below buried layer. Below buried layer also you can form a insulator layer by buried oxide using the SIMOX technology, and the side wall is already you are making the oxide. So the complete device is surrounded by a layer of oxide. So there you can prevent the junction formation, sidewall junction formation, and which will improve the speed of the circuit because of the reduction of the parasitic capacitance. These are the two advantages: increased circuit speed and increased packing density. Okay, and here the one of the as I mentioned, this in SIMOX technology, the energy used is 150 to 300 keV, and the phi means the dose is nearly 2 into 10 to the power 18 per centimeter square. So obviously, this high energy and the high dose, it will produce some damages on the surface of the crystal. And if you cannot reduce those damages, they will contribute the surface leakage currents, and the surface leakage currents will be more, and that is not good for any device. Okay, so now you have to have some techniques by which you can reduce the surface damages. So those are generally seen if the dose of implantation is very high. And not only that, this dose requires long implantation time, because if dose is more, the time of implantation is very large. So for a large time implantation, automatically the surface will be damaged, and that will contribute to surface leakage current. Now, how to reduce those damages? There is a technique, and that technique is known as high temperature implant. There what is done, the substrate is kept at a higher temperature in the range of 400 to 500 degrees centigrade. Normal implantation, we don't raise the substrate temperature. Okay, the temperature of the substrate will increase because of the impact of the ions on the surface of silicon. But here, in addition to that, before implantation, substrate is heated at temperature 400 to 500 degrees centigrade. So that will that high temperature implant obviously reduce the surface damages. At the same time, what it does here, if the substrate temperature is high, automatically the species you are implanting, that means oxygen or nitrogen, those also will diffuse more, and that means the dielectric layer may be broadened. There is one effect. Although the surface damages will reduce, at the same time the dielectric layer inside this silicon will be broadened a little bit. Okay, so that is the effect. The excessive surface damage may prevent recrystallization also. We have to prevent damages, but if you cannot, then just all implantation you have to is followed by the annealing. So that means, although the buried insulator film which you made, that is amorphous like silicon dioxide or whatever, silicon nitride, but on the top of that silicon is there, because silicon on insulator, the silicon surface layer, that has to be recrystallized again. Now that recrystallization will be prevented drastically if lot of damages are there on the surface, because on buried insulator, the silicon layer should be damage free, defect free, because there we are going to make the devices, either MOS or bipolar devices, whatever is necessary, we will make it, isn't it? So that is another problem. After implantation, to recrystallize the silicon, because it will be highly amorphous, because high dose, high energy implantation you are making, the annealing temperature is little bit higher here compared to normal dopant implantation, and that temperature is nearly 1300 degrees centigrade for several hours. And obviously you cannot use here the rapid thermal annealing. Rapid thermal annealing normally say 1 minute, 2 minutes, or 30 seconds, 45 seconds is used, but here for several hours you have to anneal it. So you have to use some furnace annealing. Okay, so now the SIMOX, I will show you after annealing how it looks like. The buried insulator, this is the TEM cross section of annealed high dose oxygen implants. TEM cross sections of annealed high dose oxygen implant. The resulting oxide layer in the second case is substantially thicker than the first case. So here you see 1100 degrees centigrade for 2 hours, and here is 14.5 degrees centigrade for 30 minutes. Their temperature is very high. And you see, this is the picture cross section TM cross section. Okay, that is tunneling electron microscopy, TEM. So that cross section diagram. So that is a real picture of a buried insulated silicon. So now this is the buried oxide, and this is the surface. And here you see the damage has not completely removed. Lot of damages are there. This is the surface layer, and this layer is the buried oxide. Now, if is annealed 1400 degrees centigrade nearly for 30 minutes, then you see here the surface quality. So this is the oxide, smooth, and here also silicon, and this side is also silicon. Silicon and silicon are very smooth here. You can see here defects what are seen here are removed in the second case, isn't it? So this is a picture of the annealing, TM picture of annealing and effect of annealing on the implanted sample. Okay. Now let us see some of the problems in case of the SIMOX. The SIMOX will again create some of the problems. What are those problems? One is heavy metal impurities, second is pinhole density, and the third is thickness non-uniformity. Fourth is material quality, and fifth is dislocation density. Okay. The problems, first is heavy metal impurities. First one, heavy metal impurities. Because if I want to have only oxide, buried oxide, so we have to prevent implantation of metal. So if you have to prevent, then no metal ion should go inside. But since the implanter machine, the chamber, lot of metals are there. Maybe steel chamber, maybe other metal chambers are there. So from those the chamber, some of the metal ions will implant into the crystal. Okay, and that will contribute in change in the conductivity, etc. So that is the heavy metal impurities lead to enhanced junction leakage current. Heavy metal impurities lead to enhanced junction leakage current. Okay. Next problem is the pinhole density. And that pinhole density due to presence of particle on the surface. The pinhole density is achieved due to presence of particle on the surface, and those particle screens oxide implant. On the surface, you say on the surface, if there is, this is the silicon surface, and if there are particles here, so for example the particle, those particles will prevent here and here implantation is done. So this portion will prevent oxygen, isn't it? So that means after the anneal, if you clean it, so then those portion will be free of the oxide particles, so some pinholes will be formed. That is coming because of the particle contamination. So you can remove that by proper cleaning. Okay, and these heavy metal impurities can be prevented by just changing the metal part of the implanter machine, by changing metal part with the quartz or silicon, because implanter machine quartz chamber is not used. If you use silicon the chamber, then from silicon metal will come, silicon will come. So if some silicon comes into the silicon crystal, it doesn't matter, isn't it? So Next problem is thickness non-uniformity. Third one is thickness non-uniformity. What thickness? Thickness of the oxide layer. Buried oxide layer, sometimes it is non-uniform. Next is material quality, that is quality of the silicon dioxide inside the bulk crystal, material quality. Okay, and because of high energy implantation, high dose, some dislocation density is found. Dislocation density means the dislocation of the crystal plane over a certain spot. So dislocation layer. So the dislocation. What is the dislocation? There is a crystallographic defect dislocation, and the different crystallographic defects I will discuss in epitaxy chapter. So there we will form single crystal epitaxy. There other defects are also there that I will discuss. That time I will clarify the dislocation. What is dislocation and how to prevent it. So in high energy implantation, dislocation are also seen. This is a crystallographic defect. These are the problems. And this SIMOX has got a lot of application in CMOS technology is present, as I told you, because it can give you the rad hard device, radiation hard device. And not only that, it will for junction isolation you can use this particular SIMOX process. And in present BiCMOS technology, BiCMOS technology, SIMOX process is used very much. And it has been reported in the literature that 256K SIMOX SRAM has already been fabricated using this technology. Okay, but here one of the primary concern of the SIMOX process is the high cost. Cost is very high. Why? Because you see, high energy and high dose implant takes a longer time, and that means a throughput here will be extremely high. So since throughput is very high, so automatically it gives the process is expensive, and cost of the device will be high. And so in order to reduce the cost, what is attempted now to have special implanter machine which can give 100 milliampere beam current. Normal implanter gives not so much beam current. So if 100 milliampere beam current is available from that machine, then automatically the time of implant will be reduced. That means you will get higher dose over a smaller time because you are getting larger beam current. So that is one of the attempt people are trying, and nowadays special implanter machines are available. Using those machines you can reduce the cost to some extent. And nowadays the SIMOX process, in the present SIMOX process, they have achieved the level of the perfectness to some extent, and it has been observed the metallic impurity is less than 10 to the power 11 per centimeter square, pinhole density is less than 0.2 per centimeter square, and thickness uniformity is nearly 50 angstrom over 6-inch wafer. These are the recent values of quality. Thickness uniformity is nearly 50 angstrom over 6-inch diameter wafer. Okay. Pinhole density is less than 0.2 per centimeter square, pinhole density, and metallic impurity is less than 10 to the power 11 per centimeter square. Okay. Now I will show you a picture of the SIMOX. Yeah, a picture of the SIMOX cross sections picture for different implantation schedule. So here you see this is a cross section. This picture is as implanted, this one, and this is the surface. This is the implanted layer, and this is again the silicon. This is silicon, this is silicon. And the surface of the silicon is magnified here. This side, this surface is small layer, this one the surface. So this surface is magnified here. You can see on the top layer silicon, how much defects are there? Lot of defects. Here you can find lot of defects. Okay. Now you anneal at 1100 degrees centigrade, then this layer has been increased. You say thickness has been increased. Earlier it was from this point to this point. Now it is from this point to this point. Thickness of the buried insulator has been increased, and the surface in this particular case is magnified, is here. Sorry, this magnification is this layer, not this one. As implanted surface is not magnified, but the second case, B case, 1150 degrees centigrade annealed sample, the surface top layer is magnified, is here, it's shown here. You can see the defects. Now if you increase the annealing temperature to 1200 degrees centigrade, then here the top layer is magnified here. Okay. Now compared to this, if you look this layer, so the defects have been reduced, isn't it? So now in the third case, again you are after 1150 degrees centigrade, again you have annealing 1250 degrees centigrade. That means two-step anneal, sequential anneal. Initially 150 degrees centigrade for some time, say 20 minutes or half an hour. Again 1200 degrees centigrade for another half an hour. That means subsequently two-step anneal. So there you can see the surface here. Top layer is, this is the top layer. Small portion this one. So it is really defect free. Very small amount of defects are seen here. And this is the insulator, silicon insulator films, this one. The oxide film is the oxide layer is here. And the third one is 1300 degrees centigrade. So there another thing, if you increase the annealing temperature to a very high value and for a longer time, then again there is a problem of forming defect. That means the annealing has got lot of effect on the surface silicon layer. There is optimum range of the temperature where you can have the defect-free surface layer. Okay. So these are the effects, and this picture is for 150 keV oxygen implant, and dose is 2.25 in 10 to the power 18 per centimeter square. As implanted and different annealing sequence, the cross section TM is shown here. Okay. Now SIMOX problems I discussed. Yeah. Now I will spend some time on few problems. This is I think the last slide here. Yeah. And before conclusion, let me conclude first. Then I will give you some of the tutorial, some problems. Problem is how the implantation problems are solved and what are the values you need for that. So now to conclude this implantation, the implantation is an indispensable technique in VLSI fabrication, a versatile tool. Ultra shallow junctions for deep submicron CMOS and BiCMOS technology, implantation is must, and implantation is followed by RTA, rapid thermal annealing. And another application of implantation is high energy, high dose oxygen and nitrogen implant for SOI, just now I discussed. And a recent trend is low energy, high dose and low temperature implant. Low energy, high dose is for shallow junction formation. Okay. In case of SIMOX, sometimes the furnace anneal is used. Rapid thermal anneal may not be sufficient, may not be adequate to remove all the defects. Now, I will discuss on some one or two tutorial problems on implantation. Now, before going to that, let us see here. So, the normal ions which are implanted, this table is very important and it will give you some of the information. And these results are obtained from Monte Carlo simulation. And here I have shown the values of Rp and delta Rp. Rp is the range and delta Rp is the straggle. And the ions I have used is boron, phosphorus, arsenic and antimony. Target is silicon. Silicon will have mass number 28. In the top written the mass number and Z is written at the bottom. Z is the atomic number and the atomic mass. In boron, atomic mass is 11 and atomic number Z is 5. In phosphorus, atomic mass is 31 and Z is 15 atomic number. Arsenic, atomic mass is 75 and Z is 33. Antimony, atomic number is 122 and Z is 51. Okay. Now, the parameters I have calculated is Rp and delta Rp. And three energies are used: 10 keV, 30 keV and 100 keV. If you look the values in this table, then you will find that boron in the same energy of implantation, say 30 keV, 30 keV is the normal implantation energy which is used for device fabrication, 30 keV. Boron implantation gives the Rp 1065 angstrom, whereas phosphorus gives Rp 420, arsenic gives 233 and antimony gives 208 angstrom. So 1065 angstrom is how much micron? 0.1 micron. So here you are getting 0.1 micron, here is 0.04 micron, here 0.02 micron, here 0.0208 and 0.0233. Now, what is Rp? You remember Rp is the peak concentration. From the surface, at Rp depth, you will have the peak concentration. That is Rp. If you remember the curve, the profile, LSS theory or that, isn't it? Now, the peak concentration means the peak concentration junction or peak concentration depth from the surface reduces if you increase the mass number of the dopant. So here it is the mass number 11, this light impurity, mass number 31, here is mass number 75, heavy ion, arsenic, and antimony 122, heavier ion. So from 11 you can have 0.1 micron. If you use phosphorus whose mass number is only 31, it will give you 0.04 micron. In case of arsenic, it is only 0.02, isn't it? So, and delta Rp is the straggle, and straggle is also reducing if you use ions of heavier mass. The straggle values also, and all the energy, and also if you increase the energy, it is seen that the Rp also increases. You see here for 10 keV 0.038 micron, 30 keV 0.1 micron, 100 keV 0.3 micron. That is also as expected. If you increase the ion energy, this increases. And if you increase the mass of the ion, impurity ion, then obviously Rp value reduces, say 82 angstrom to 150 to 110 to 100. Okay, and the target atoms is silicon, or if you use germanium, then mass number of silicon is 28, its atomic number is 14. In germanium, mass number is 72, atomic number is 32. Basically, this 4 and this 2, 6, this 6 element, mass number and atomic number, you should try to remember, because these are the common elements which are used in implantation or used in devices. Now, one problem is here, written problem 1, you can see a 30 keV implant of boron B11 is done into silicon. The dose is 10 to the power 12 per centimeter square. What is the depth of the peak of the implanted profile? What is the depth of the peak of the implanted profile? What is the concentration at this depth? What is the concentration at a depth of 3000 angstrom, means 0.3 micron? If you remember the profile I am drawing here, so roughly it is something like this. A full Gaussian, this is a x, and this you plot as nx, x and nx. Okay. So now here this particular point give you, this is what? This is RP. So the peak concentration will be at RP depth. What is the depth of the peak of the implanted profile? That means RP value will be the depth of the peak of the implanted profile. It is ideal double-sided Gaussian. Okay. Now, the profile here is given by nx is equal to phi divided by under root 2 pi delta rp exponential minus x minus rp squared to delta rp squared. That has been shown in the discussion on the theory of implantation. That relation already I told you, isn't it? So here, what is the phi? Phi is the dose, rp is the range, and delta rp is the projected range or straggle. The delta rp, this one, is the projected range or straggle. So that means this expression contains the dose term, projected range, range and projected range. Projected range is a straggle, which is delta rp. And this rp is given by integral of d by Sn plus Ac, where Sn is the nuclear stopping potential, Ac is the electronic stopping potential. Now the electronic stopping potential Ac is again given by Ke into under root E. So Ke is again given by under root Zi Zd Mi3 Mt, where I stands for ion and T stands for target. Mi plus Mt to the power 3 by 2 divided by the Zi to third plus Zd to third. This is a Ke. Then this Se is function of the energy. Electronic stopping is a strong function of energy. I mentioned that point also. And nuclear stopping is a weak function of energy. And the Sn is given by the maximum nuclear stopping power, Sn0, this maximum value is given by 2.8 into 10 to the power minus 15 electron volt centimeter square into Zi Zd divided by Z to the power 1/3 into Mi divided by Mi plus Mt. Okay. So this is the maximum Sn value, and this is the Ac value. So Sn and Ac you put it here, then you have to integrate from 0 to E0 to 0. 0 means it will stop That means here energy is 0, where it will stop. So now all these calculations are involved. So those calculations normally, if you do the integration, and this here again, this is the higher value, it's not function of energy. So those are some tables are available, or you have to calculate this using the Monte Carlo simulation calculation if you want to exactly find the RP and delta RP. And delta RP is again related with RP by this relation. You see, delta RP is given by this relation. Delta RP is equal to 2/3 RP under root mi mt by mi plus mt. I stands for ion, T stands for target. M is the mass number and Z is the atomic number. And atomic number and mass number are given in that earlier table for the commonly used ions and targets. Targets are, as I told you, silicon or germanium target, and ions are boron, phosphorus, arsenic, antimony, etc. Now, in this particular problem, the problem 1, so there first is what is the depth of the peak of the implanted profile, that is the RP value. And that RP value, if you want to calculate, then you need lot of information. So there the boron atom mass number is 11, and its what is the Z of boron is 5. So that is known. Okay. Now next is if you know the RP value in this expression, you see this expression is here. Here if you know the RP value, then delta RP easily you can calculate using this relation, because mi is known, mt is known, RP is known, delta RP you can calculate. So RP known, delta RP known in this equation, RP known, delta RP known. Phi is given, how much it is? 10 to the power 20 per centimeter square. So phi is given. So easily you can calculate the nx at a particular x. So that means the second part of the problem is what is the concentration at this depth. So that means what is the depth? Depth is the peak. So at the depth, what is the x? X equal to RP. So at this peak concentration will be at x equal to RP. So that means if you put x equal to RP, then this vanishes. So only this term is there. So that means the concentration at this peak, the peak value of the concentration at x equal to RP is given by phi by 2 pi delta RP. So you will be able to calculate now. Phi is given, delta RP value will be given. RP value is a range for 30 kV boron is shown in the earlier table. So the boron is here. RP in the 30 kV is 1065 angstrom unit. So you have to consult the table. Okay. Now this is calculated. Second is what is the concentration at a depth of 3000 angstrom. This is 0.3 micron. So that also from this relation you can calculate. Once you know this value, this is a peak concentration is known, then at 3000 angstrom means if x equal to 3000, xp is known, delta RP known, nx you can find it out. Clear? So that means for the calculation of this problem, or for solving this problem, you have to have the value of RP I have to provide. The another problem is a mass spectrometer is used for element extraction in an implanted. Calculate the magnetic field energy necessary to extract silicon if the extraction potential is 20 kilovolt and the radius of curvature of the analyzer is 30 centimeter. The second problem is mass spectrometer is used for element extraction in an implanter. Calculate the magnetic field energy necessary to extract silicon if the extraction potential is 20 kV and the radius of curvature of analyzer is 30 centimeter. Here not impurity, they want to extract the silicon, and that is there the relation is R equal to 1 by B under root 2 m by q V external, that is V external is the 20 kilovolt. Okay. So there 1 by B under root this, that means here the R is the 30 centimeter, that is given. M is equal to mass in case of silicon is a 28 is the mass number. 28 into 1.67 in 10 to the power. What is the mass number? This is something wrong, not -2, -31, yeah. This will be 31. 1.67 10 to the minus 31 kg here. This will be 31. Okay. Q is equal to 1.6 10 to the minus 19 coulomb, and external extract potential is 20 kilovolt, that much volt. Then what is the value of the B? You have to find. And B will come in Tesla. And you have to convert in kilogauss. 1 Tesla is equal to 10 kilogauss. So here you see R is given, M is given, Q is given, V external is 20 kilovolt. You can easily calculate B, magnetic field. 27. 1.67 in 10 to the power. If it is in for oh, so that is the 27. Or that 7 I missed here. 2 I have written. It will be 7 here. That is M is equal to 28 into 1.67 into 10 to the power 27 kg. Okay. So this is the mass into 28. 20 is silicon. Okay. So let me stop here.